Ladies and gentlemen, welcome to the next webinar in the Coffee Breaks with NenoVision series. This webinar shows the advantages of combining AFM and SEM systems for focused ion beam applications. And of course, we'll be glad if you stay with us until the end of the whole webinar series. The last webinar is happening next Thursday on July 16th and will show you measurement tutorial using LiteScope. As always, you can only ask questions using the Q&A chat window, and since the slides are pre-recorded, I can answer your questions during the stream. And if there are going to be any important questions, I will answer those on microphone by the end of the webinar. Enjoy the presentation. Welcome to this webinar, dealing with the benefits that come from connection of an atomic force microscope with a scanning electron microscope equipped with focused ion beam. Atomic force microscopy and focused ion beam generally existed separately. The following slides show that the integration of a compact AFM into focused ion beam SEM can marry all three complementary techniques and that their combination can result in unique capabilities unachievable with any of those techniques separately. Focused ion beam sources coupled with scanning electron microscopy have drawn significant interest due to their unique ability to generate a variety of structures, whether through milling or ion beam induced deposition, while being directly observed via SEM. Focused ion beam generally consists of an ion source, a series of electrostatic lenses to shape the beam, and a scan generator to guide the beam onto a sample with a moving stage. In a typical dual platform instrument, an electron column is mounted vertically and the ion column is mounted at an oblique angle, normally between 45 to 55 degrees. Most commercial FIB microscopes are currently equipped with a liquid metal ion source emitting gallium ions because of the robustness and other advantages associated with this technology. However, there are now several alternative ions available via different sources for FIB microscopes, offering a large range of available ion currents, energies, and beam sizes, which is important to various niche applications and higher resolution patterning. The focused ion beam microscopes have been used most significantly in the semiconductor industry, but also in various material and life science applications. What is actually LiteScope? LiteScope represents a unique atomic force microscope which is designed to be easily integrated into a variety of scanning electron microscopes. And since LiteScope can be tilted, it is fully compatible with focused ion beam, gas injection system, EDX, and other standard SEM accessories. Why to actually combine AFM and SEM systems? Atomic force microscopes and scanning electron microscopes are two of the most used and in fact complementary techniques for sample analysis in the nanoscale. Nevertheless, since the principle with which they observe and interact with the sample surface is completely different, they provide a very different set of information. AFM monitors an interaction between a physical probe and sample surface and for that reason represents a tool of choice for topography and roughness measurement with sub-nanometer resolution. AFM also enables analysis of mechanical, electrical, and magnetic properties. On the other hand, scanning electron microscope observes and analyzes the sample surface using a focused beam of electrons. This interaction produces various signals, so besides fast 2D imaging in wide range of resolutions, SEMs can provide information on sample composition as well. Further possibilities of SEMs, such as surface modification or nanomanipulation, will depend on their additional accessories. With that being said, the motivation behind LiteScope design is as follows. First, the AFM and SEM approach allows for efficient yet complex in-situ sample characterization that combines capabilities of both techniques. And second, it brings completely new possibilities for advanced correlative imaging, which allows analyzing samples in a way that was difficult or even impossible by separate SEM and AFM systems. As an example of the correlative capabilities of LiteScope, let's have a quick look at the correlated three-dimensional image in the middle of the slide. The correlated image clearly provides more information about the sample that would have otherwise been possible using each imaging modality separately. CPEM stands for Correlative Probe and Electron Microscopy. This technology is unique to LiteScope and was developed for seamless data correlation. So let's have a look on how it actually works. So on the sample, the electron beam points close to the AFM tip with a constant offset. And during scanning, the AFM tip and electron beam remain static. Sample is being scanned only by the LiteScope piezo scanner. And this enables simultaneous detection and acquisition of AFM and SEM signals at the same time, in the same place, and under the same conditions. The development of combined focused ion beam and scanning electron microscopes has enabled significant advances in the characterization of 3D structures of materials. However, as any technology, FIB and GIS systems come with challenges, partially arising from the limitations of SEM systems. So although focused ion beam surface modification is very precise, it is not possible to accurately determine the depth of the sputter structure, as the sputter speed depends on the chemical and crystallographic composition of the sample. This issue gets especially pronounced with heterogeneous materials. Besides topography and roughness evaluation, LiteScope possesses a variety of measurement modes for comprehensive three-dimensional reconstruction of the FIB and GIS structures, including measurements of mechanical or electrical properties. Then, the FIB milling can be combined with the topography measurement simultaneously to in time calibrate the process for precise patterning and desired depth. And lastly, as we will see later in the presentation, the AFM and FIB data can be used to optimize the milling rate for various materials and ion sources. The multimodal analysis using an addition of high vacuum compatible AFM can elevate the already mentioned limitations, but also enables to combine the capabilities of all three systems. And this combination opens up the possibilities of sample analysis that were not possible by separate AFM and FIB-SEM systems. Let's have a look at the main LiteScope benefits for focused ion beam applications. It is extremely useful to utilize SEM for precise AFM tip navigation to the region of interest. Next point is sub-nanometer three-dimensional profiling of nanostructures in in-situ conditions, which is crucial for FIB surface modifications and also for sensitive samples. Information about the planarity and surface roughness during or immediately after the FIB milling is extremely useful, predominantly in the semiconductor industry. Then, direct AFM analysis of FIB and GIS modified surface enables to optimize the process for various materials and ion sources. And lastly, it allows for in-time AFM and SEM data correlation by already mentioned technique we call CPEM. In the split screen, you can see precise AFM tip navigation using SEM and LiteScope in tilted position, which also reveals the AFM tip in contact with the sample. The second part shows positioning of the electron beam right next to the AFM tip for simultaneous AFM and SEM data acquisition using the correlative CPEM technology. Now let's talk about the main application areas for combined AFM and focused ion beam SEM instruments. Let's start with the most straightforward feature of integrating AFM within SEM equipped with focused ion beam, which is in-situ topography and height profiling of FIB and GIS structures. Depending on the application, the AFM topography analysis can be performed during or right after the FIB processing. In this setting, breaking the vacuum is completely eliminated when alternating AFM measurement with FIB processing, which is crucial for sensitive samples as oxidation can occur. Additional advantage of in-situ AFM is higher quality factor compared to standard in-air AFM. The AFM tip can freely vibrate in vacuum conditions, and thus the sensitivity to surface variation is increased. Another important feature of combined AFM and FIB-SEM systems is roughness evaluation of the bottom of the milled structures. And for this purpose, I'm going to show application where LiteScope was used to evaluate failure analysis of integrated circuits. The sample is 40 nanometer technology node Intel processor composed of multi-layer structures that contain multi-gate transistors as key elements. A failure analysis process of such integrated circuits typically involves delayering and electrical nanoprobing. So far, delayering has been performed mainly by means of mechanical polishing. However, for future devices, mechanical polishing cannot be used due to micro and nanomechanical deformation and chemical interactions with the polishing suspension. Here, LiteScope was used for in-situ roughness analysis of individual layer interconnections for failure analysis and quality control purposes. The integrated circuit was FIB milled layer by layer, and each layer was scanned by LiteScope and the SEM. Subsequently, AFM and SEM data were correlated by the CPEM technology for better data interpretation. Complete analysis, including depth profiling and roughness measurement, was performed in in-situ conditions to prevent surface contamination and oxidation. The combination of three techniques, focused ion beam, SEM and AFM, was used for complex analysis of the integrated circuit. The SEM was used to control the delayering process, to precisely navigate the AFM probe, and to provide the material contrast. AFM provided information about the planarity and surface roughness of each layer. This application demonstrates how the combination of AFM with SEM equipped with focused ion beam can be utilized to optimize the focused ion beam milling process. And for this purpose, cadmium telluride was sputtered using increasing doses of ions as depicted in the SEM image. Each of the 10 frames were immediately analyzed by AFM and SEM in in-situ conditions. The AFM and SEM data were correlated using CPEM technology and used to optimize the FIB milling process. First, LiteScope was used to precisely analyze the sputtering depth versus ion intensity to optimize the sputtering time. This characteristic can be done for any material and ion source. And because cadmium telluride represents a heterogeneous material, AFM roughness assessment was performed to achieve the desired surface profile. Cadmium telluride represents a sensitive sample, and an AFM analysis of one of the FIB mill structures demonstrates the importance of in-situ conditions. Both the AFM topography and the measured depth profile shows the sample oxidation over time when exposed to atmospheric conditions. According to this analysis, tellurium inclusions oxidized within a few minutes with saturation after several days. Towards the end of this presentation, I will show two applications where the focused ion beam wasn't used primarily for material microstructuring, but rather as an analytical probe. In this application, focused ion beam was used to study direct magnetic patterning. Thin film of iron-nickel alloy was grown on silicon substrate. This film undergoes a magnetic and structural phase transformation upon ion beam irradiation, and thus can serve as a template for direct writing of magnetic nanostructures by the focused ion beam. Multiple spots in the alloy were focused ion beam milled using increasing doses of ions as depicted in the AFM and SEM images. The phase transformation is nicely visible in the highlighted squares. Using LiteScope and CPEM technology, it was found that the material transformation is accompanied by topography changes in the range of a few hundred picometers. In this case, the step between high and low magnetic moment was 470 picometers high, as depicted in the height profile. For better data interpretation, the CPEM view was used to merge the topography and material contrast. Additionally, this alloy represents a sensitive sample prone to immediate oxidation, and for that reason, this application could not be done by using separate AFM and FIB-SEM instruments. Time-of-flight secondary ion mass spectrometry, or shortly TOF-SIMS, is a very sensitive surface analytical technique well established for many industrial and research applications. The measurement principle is based on local sputtering of the sample by focused ion beam while collecting and selecting the sputtered ions according to their mass. Its sensitivity makes it suitable for local trace element important to detect impurities in semiconductors and metals. This technique is also capable of analyzing the chemical composition of multilayer structures. However, this technique doesn't allow to determine the depth of the sputtered particle because, as we have seen in the previous applications, the sputtering speed can vary significantly on heterogeneous materials, but also with changing depth of the sputtered structure, and therefore additional in-situ analysis by integrated AFM is required to calibrate the topography of the sputtered structure and to analyze the roughness of the crater bottom. LiteScope integrated into FIB-SEM's system was used to analyze the sputtered structure each 500 frames, and the resulting topography was subsequently correlated with the elemental map provided by TOF-SIMS and SEM material contrast. The result of the elemental analysis were three maps: AFM topography with height profile, material contrast provided by SEM. SEM was also used to precisely navigate the AFM probe. And lastly, the elemental distribution by SIMS. The biggest challenge for TOF-SIMS technique is to be able to accurately determine the depth from where the signal came from. And the demonstrated combination of AFM and TOF-SIMS techniques clearly shows its potential in that manner. The consecutive sputtering and AFM topography analysis is advantageous especially for heterogeneous materials that do not sputter evenly. In this early stage, it was only possible to correlate the AFM topography with SEM's material contrast to create a comprehensive three-dimensional view of the sputtered crater that can be further compared to the lithium and aluminium distribution provided by TOF-SIMS. In future, further correlation of these techniques will provide detailed depth-correlated three-dimensional elemental distribution. Further advantages of this hybrid technique include the potential for sputter rate optimization, even though this was out of the scope of this application, and additionally, the surface oxidation was avoided thanks to the complete analysis in in-situ conditions. The LiteScope incorporates innovations in design of atomic force microscopy, enabling its integration with SEM and focused ion beam systems into a single powerful analytical tool. The key prerequisite for full compatibility of LiteScope with focused ion beam applications is its ability to tilt into a typical FIB milling configuration where the sample surface is normal to the incident ion beam. The biggest advantage of combining AFM with focused ion beam is the direct monitoring of nanofabrication process in in-situ conditions and three-dimensional reconstruction of the modified structures. Besides topography, LiteScope supports variety of measurement modes and hardware data correlation using the unique CPEM technology for multimodal sample characterization and correlation of such data. As we have seen in the presentation, the AFM topographic analysis can be used to optimize the focused ion beam milling process and to correct roughness for heterogeneous materials or for samples with more complex surface topology. And lastly, majority of the presented application examples show that the addition of complementary AFM to FIB-SEM systems is way more powerful than each of those techniques separately, and that these applications could not have been accomplished otherwise. And with that, I would like to thank you for your attention.
So now we are starting the Q&A section. We have one interesting question that I feel is better to answer on the microphone. And the question is, if you scan by AFM in between focused ion beam milling, will the AFM tip get contaminated? So the answer is not necessarily, because you can either move the tip away or you can even home the tip to save position. So with that, I would close the Q&A section. And if you have more questions, please visit our webpage, nenovision.com, or you can also contact us directly via email. And again, I will invite you to the next webinar, which is going to be the last webinar in this webinar series. And this one will be hosted by my colleague, our application specialist, Veronika Hegerova. And this one will be focused on the measurement tutorial with LiteScope. And again, it's streaming on July 16, next Thursday. With that, we are coming to the end. And as always, on behalf of the whole company, I would like to thank you for your attention and see you at next webinar. Bye.